Hey there, physics students. So in our unit about momentum here, we've talked a little bit about momentum. We know that momentum, P, is equal to the mass times the velocity, P equals mv. We know that it's measured in the units kilogram meters per second. And we've talked about the impulse momentum theorem. And today what we're going to do is we're going to go ahead and we're going to talk about collisions and the conservation of momentum. When two objects collide, in order to predict what's going to happen to them, you want to take a look at their momentums. And so we're going to go ahead, we're going to talk about conservation of momentum and what happens when two objects collide. So our target is to be able to solve conservation of momentum problems. So let's go ahead and let's take a look at some of that and talk about what that means. Okay, let's go ahead and develop this idea of conservation of momentum. Let's say that I have two objects that are going to collide. Okay, here I have object 1 and here I have object 2, and they're going to collide with each other. Okay, well, conservation of momentum is this idea that the total amount of momentum in this system is going to remain the same before the collision and after the collision, which means if I add up their momentums before they collide, that should be equal to if I add up their momentums after they collide. So let's do a little bit of math here and derive an equation to describe the conservation of momentum. So what we're saying is that their momentums before the collision equal their momentums after the collision. So for my object 1, its momentum before the collision, I'm going to call that P1I. Right? So the momentum of object 1 before the collision, the initial momentum of object 1. And I'm going to add to that the initial momentum of object 2, which I will call P2I. Okay, so that's the total amount of momentum before the collision. And that should be equal to the total amount after the collision. So let's say object 1 has a momentum of P1F after the collision, so the final momentum of object 1. And object 2 will have a momentum of P2F, so the final momentum of object 2. Okay. Now we know that momentum is mass times velocity, P equals mv. So let me go through here and let's substitute out the P for an mv, right? Now, over the course of the collision, usually in our collisions that we're going to talk about in physics class here, the mass of objects doesn't change, okay? But their velocity will. So for the momentum of object 1, for the initial momentum of object 1, I'm going to say that its mass is m1. It's the mass of object 1. And its velocity, because it'll change, I'll call this its initial velocity. So I'm going to call this v1I. The initial velocity of object 1. And I'll do the same for object 2. Its mass will be m2, and its initial velocity, I'll say, is v2I, the initial velocity of object 2. And then over here on the other side, for the final velocity of object 1, since its velocity changes but its mass doesn't, its mass is still m1, but now its velocity is v2f. I'm sorry, v1f, because we're talking about object 1. And for object 2, its mass is still m2, but now its velocity is v2f. There's the v2f. Okay. And this right here is the equation that we use to solve conservation of momentum problems. Let's go ahead and look at some of those problems. Okay, let's go ahead and take a look at a problem here, and I'll show you how I like to show students how to solve these problems. The problem, it says a 76 kilogram boater initially at rest in a stationary 45 kilogram boat steps out of the boat and onto the dock. If the boater moves out of the boat with a velocity of 2.5 meters per second to the right, what's the final velocity of the boat? Now, one thing you got to kind of keep in mind is that not all collisions are like a car crash, right? So here I have a guy stepping out of a boat. That's a collision, okay? if I have a guy jumping into a boat or jumping onto a skateboard or jumping out of a car or something, that's a collision. It's whenever two objects come together, separate, something like that. So let's take a look at this. First thing we need to do is we need to identify what are our two objects. And what I like to do is I like to write down two lists, one list for the first object and one list for the second object. So here in my example, I have a boater and a boat. And those are my two objects. So I'm going to pick one to be object one. It doesn't matter which one is object one and which one is object two. Just pick one to be object one and the other one to be object two. So I'm going to say object one is the boater. Object one is the boater. And object two is the boat. Doesn't matter which is which, just pick. Okay, now what I'm going to do is I'm going to list the information for each one. Each one of these has a mass. This one will be M1. This one will be M2. Each one has an initial velocity. This one will be V1I. This one will be V2I. And each one has a final velocity. This one will be V1F. And this one will be V2F. Okay. And 5 of these 6 numbers should be found in the problem. Sometimes objects end up having the same initial velocity to begin or the same final velocity to end. So you have to be careful for that. So 5 out of these 6 numbers should be in the problem. They might not all be explicitly stated. So sometimes you have to read some things into the problem. So let's see what we can find. For the mass of the boater, the problem says it is 76 kilograms. So that's easy. And the boat, it says, was 45 kilograms. So also easy. Okay. Let's see. It says that he steps out of the boat onto the dock. Okay. So I think we can assume that both the boater and the boat were moving the same speed and it was 0. Because usually you don't step out of a moving boat. I mean, if you step out of a moving boat, you're likely to get wet. So I'm assuming it was stopped at the dock. So let's say their initial velocities, both 0. Okay. Now it says the boater stepped out of the boat with a velocity of 2.5 meters per second to the right. Okay. So let's say to the right is the positive direction. We have to be very careful with direction here. Okay. So we'll say that 2.5 meters per second to the right was in the positive direction. Okay. And it says, what's the final velocity of the boat? So this is what we're looking for. Now, if you just think about the situation for a minute, you step out of a boat going this way. Which direction do you expect the boat to go afterwards? I would expect it to go the opposite direction. So when I get my answer here, I expect this to be a negative because it should be going in the opposite direction. I have to be very careful with direction here, okay? Now I'm going to take these numbers, I'm going to put them into the equation we derived, and I'm going to solve for the thing they asked me to find. So M1 was 76, and V1I was 0. I like to put these in parentheses, separated by a plus, because it kind of helps me like visually keep track of each of the 4 terms in there. Okay, M2 was 45, and V2I was 0, equals M1, again, was 76, times V1F, which was 2.5, plus, and then we've got M2, which was 45, times V2F, which is what we don't know. So I'm going to write V2F. Okay. Now we need to solve the equation. And this one's fairly easy to solve because this and this are both 0. So 0 equals, let me see, let me grab my calculator. I have 76 times 2.5, which gives me 190. Keep in mind they both have 2 significant figures, so this one has 2 significant figures. And here I have 45 times V2F. Let's subtract this to the other side over here. So this will be negative 45 V2F. And over here I have 190. And then we'll divide both sides by that negative 45. So V2F equals negative, let's say I need 2 significant figures, so I'll round that off to 4.2. So negative 4.2. And since this is a velocity, meters per second. Okay, so the answer sort of makes sense. We expected it to be negative. We expected it to be in the opposite direction of the boater's initial velocity, right? The boater had a higher mass than the boat, so I can expect the boat's velocity to be higher than the boater's velocity. So the answer makes sense to me. So here's an example of using the conservation of momentum equation. Now, I would highly suggest that you when you're doing your work, write out which object is object 1, which object is object 2, make your little list of terms and what each one is equal to, and then show your work to solve the problem. Okay, make a very organized way of doing it because there's a lot of information in these problems. They're not that hard, there's just a lot of information. So having a nice organized way to keep them is a good idea. Okay, so there's a little bit about collisions and the conservation of momentum. Hopefully that helps us be able to solve problems with the conservation of momentum. Yeah, until next time, take it easy.